Okay, so let's use this to solve a few examples. The first is an example of a ceiling fan. So we have a ceiling fan that's starting from this condition. It's initially at rest, and at t equals 0 it's turned on, and the electric motor starts giving it a torque, and it causes it to start turning. So initial speed is 0, then the speed starts to increase at a rate of an angular acceleration of 0.2 radians per second squared. The question is, what is the omega, or the angular speed, after 10 seconds? So we use the first equation, omega final equals omega initial plus alpha t. Omega final is what we're looking for. Omega initial is 0, initially at rest. Alpha is 0.2 radians per second square, and the t is 10 seconds. So one of the seconds cancels. We're left with radians per second, and this gives us 2 radians per second. So after 10 seconds, the speed will be 2 radians per second. Now, how much angle has it turned in this time? So we use the other equation, and the theta initial we can take as 0. We can say wherever it started from for one of the wings, we can take that as 0. Initial speed was again 0, and we plug in the rest of the things and we get 10 radians. So it has turned by 10 radians. Now 360 degrees is 2 pi radians, which is around 2.68 or so. So that means 10 radians is more than one full circle. So this wing would have made one full circle, and it's about somewhat more than that. So the next thing is, well, how many revolutions did it make? How many times did it make complete circles? So we know that 2 pi radians is 1 revolution, or 1 complete circle is 360 degrees, which is 2 pi radians. So 10 radians would be 1 revolution over 2 pi times 10. The radians would cancel, we get revolutions 1.59. So that means that it makes 1 complete and half and a bit more than that. So it turns by that distance. So we get the delta theta, the revolutions, and the angular speed. Now let's solve another example, and this one is for a CD, and this is also in the textbook. So if we have a disc, it could be a CD or a DVD, and it has tracks on it. So as it's spinning, the innermost track would be here. Well, there's a hole in the middle, and then the outermost track would be somewhere here. Now the laser is touching it here, the disc is spinning, so the laser would move over a surface, and the data is written in a number of tracks. So the innermost track is here. The radius of the innermost track is 23 millimeters, and the radius of the outermost track is our outer, which is 58 millimeters. Now, the way it's made, a certain distance contains 1 byte of data, and we want that distance to be the same here, here, and also here. So the distance in which a byte of data is written should be the same. So when the laser beam is here, and if it's spinning at a constant speed, it will cover some distance, but when it comes here, it will cover less distance in the same time, because omega is the same and v is smaller. So that doesn't work. So what we want is that the v should be the same. So when the laser is here, the v is the same, so it covers a certain distance in a certain time. When it's here, it covers the same distance, so the v should be smaller. The v should be the same, omega should be smaller. And this v is 1.3 meters per second, and that's a CD. Now, using v equals r omega, we can get omega is v over r. So omega, when it's at the inner location, is V is 1.3 meters per second, and the radius is 23 over 1,000 meters. The meters will cancel, and 1.3 over 23 comes to 56.5, and it's only per second, but we write it as radians per second to indicate that it's an angular speed, even though the radians are not visible here. Or you can see the meter per meter is a radian. Then the omega at the outermost track, there's a number of tracks here, so the outermost track is going to be the same speed, and it's now 58 meters over 1,000, 58 over 1,000, so 58 millimeters, and this gives us 22 radians per second. Now, if you want to convert this omega from radians per second to revolutions per minute, or RPM, then let's do it for the first one. So it's 56.5 radians per second. We divide it by 2 pi to convert it to revolutions, and that's per second, so that's a radian per revolution, and we multiply with 60 seconds per minute. The second will cancel, the radian will cancel, we're left with revolutions and minutes. So when we solve this, we get 540 RPM, revolutions per minute. So when we are on the 56, that's the inner track. So when we are at the inner track, it's spinning at 540 RPM, and when we are at the outer track, so we do the same thing we did here, multiply with 60 over 2 pi, and that comes to 210 RPM. So when you're here, it's spinning at 210 RPM. So the disk keeps getting faster and slower, so that the V always remains the same. Now let's do another example, and 3, and we have a car that's going at 60 miles per hour. So mph is miles per hour. What is the angular velocity of its wheels? How many radians per second are the wheels turning? And we can say the radius is 40 centimeters. The diameter is about 80 centimeters, which is sort of reasonable. The first thing to do is to convert the 60 miles per hour into meters per second. So it's 1609 meters per mile. Cancel the mile, and we're left with meters per hour. Now we change the hour to seconds, so there will be 1 hour is 3,600 seconds. So the hour will cancel, and this time this divided by 3,600 comes to 26.82 meters per second. So that's the speed with which the car is going. Now, one circumference of the wheel is 2 pi r, and that's going to be 2 pi times 0.4 meters. So that's going to be 2.513 meters, which means that if the wheel were here and this was a point on the wheel, as the wheel goes forward, this point will go around a circle, and by the time it touches the ground again, the wheel has moved forward by 2 pi r meters by the time the wheel makes one circle. So if one circle is so many, or one revolution is so many meters, so in 1 second it goes 26 meters. So how many revolutions? So the number of revolutions it makes in 1 second is going to be the distance covered in 1 second, which is 26.82, divided by how much it needs per revolution. So that's meters per second divided by meters, so it's just per second. and this is now revolutions, because this is meters per revolutions. We could put a per revolution here and we'll have a rev here, and this 26 over 22.5 comes to 10.67 revolutions. Now, because we want omega, and omega is radians per second, we have to convert this into radians. So we multiply with 2 pi, and we get 67.05 radians. And since all of it is per second, that's also per second. And so that's our answer, that omega is 67.05, so 67.1 radian per second. We could also have done it much easier, say V equals R omega, and therefore omega is V over R. The V is 26.82 meters per second, and the radius is 0.4 meter. The meters would cancel, and 26 over 0.4 is 67.05, and the units would be per second only. But we know that it's omega, so we just make that as radians per second, because the meter over meter in this case is a radian. So we get the same result in a much simpler way.